Welcome to the Real Science of Time Travel, with me, Dr. Dan Stokes. Part 2, Changing Time. The foundations of time travel are in quantum mechanics. Quantum states evolve unitarily according to the Schrödinger equation. Unitary evolution is reversible, i.e. there's no information loss, according to the Schrödinger equation. Measurements update our knowledge, but do not necessarily update the state of the universe. Interpretations differ, therefore, on how outcomes appear definitive. The many worlds theory proposed by Everett in 1957 states that the wave function never collapses. This decoherence explains why branches don't interfere. Time travel that changes events merely places you in a branch where those events differ. Time travel, according to this theory, is therefore possible. Experiments using delayed choice quantum erasers have shown that choices made after a photon passes a slit can determine whether interference appears in a conditional distribution. This looks retrocausal, but does not enable signaling to the past, i.e., the no communication theorem holds. Causality in quantum mechanics is subtle but intact. This again suggests that time travel is possible. Seth Lloyd and colleagues modelled time travel via quantum teleportation plus post-selection, effectively keeping only histories that are self-consistent. Lab-scale photonic experiments have demonstrated analogues of this behaviour. Again, no paradox, but also no free lunch. You cannot send usable information to your own past without paying consistency constraints that, in practice, block contradictions. Hawking argued that quantum fields in space-time develop divergent stress energy, which would gravitationally back-react to destroy any incipient time machine. In semi-classical gravity, vacuum fluctuations amplify without bound. This theory essentially states that the laws of physics conspire to prevent macroscopic time machines. It's a conjecture, but every attempt to beat it runs into instabilities, energy blows-ups, or require exotic matter. So what about black holes? The Hawking temperature for a Schwarzschild black hole is around 10 to the minus 8 Kelvin, basically near zero. These are not time machines, but they are superb time dilators. If you were to orbit close to the innermost stable circular orbit, decades would pass while months pass for someone else, depending on the spin of the black hole. Some physics say you could, in principle, navigate a black hole. However, realistic astrophysics say tidal forces, radiation, and instabilities would shred you long before that. Black holes evaporate by quantum effects near the event horizon. If information were lost, unitarity would break, contradicting quantum theory. Modern consensus is that information escapes subtly. Why does this matter for time travel? Well, if information cannot be destroyed, sending it to your own past risks double counting, which must also be avoided. Consistency constraints pop up again. Time travel must maintain the allowed processes, i.e. those that keep global unitarity intact. So, what practical time travel can we do today? Flying commercial airliners can produce microsecond-level time travel via velocity effects. Moving up a staircase, going 2 steps or around 30 centimetres, you will time travel by gravitational effects to around 10 to the minus 18 seconds. Particle beams, storage rings in accelerators like the Large Hadron Collider, routinely produce time dilation factors at giga-electron-volt energies. This is effectively everyday future time travel for ions and muons. One of the key questions when it comes to time travel is, would changing the past destroy my free will? Do I have a choice, or are my decisions already predetermined? Some physicists say that past, present and future coexist in a 4-dimensional manifold. Free will becomes an emergent description of agents embedded in this block. In the many worlds theory, free will corresponds to branching. You experience one branch while others exist. According to Novikov, your choices are, and were always, part of a consistent loop. None of these physics forbid meaning or agency of your free will, they just recast it. So while we're on that topic, what about the ethics of time machines? If paradox-free, but branch-creating travel were possible, then sending information back would create new timelines with divergent histories. In this situation, who authorises or governs timeline-creating actions? How do you prevent branch explosions from uncontrolled experimentation? If future tech can rescue past disasters in new branches, do we have a moral duty to try? Or do we have a duty not to interfere in the past timeline? These are all science fiction questions for now, but they illustrate why chronology protection might be more than physics. It may also be a cosmic ethical safeguard. So, which sci-fis get the physics right, and which sci-fis get it wrong? Time travel has been science fiction's favourite playground for nearly a century. Every story builds its own rules, but physics doesn't always agree. Let's separate which sci-fi nails it, and which bends it beyond recognition. We'll start, of course, with Back to the Future. A DeLorean, 88 miles per hour, and one of cinema's most iconic paradoxes. Back to the Future uses a single mutable timeline. It changes the past and your present vanishes. That makes for great tension, but the physics disagrees. Einstein's relativity doesn't allow a universal now to rewrite. If you could travel to 1955, you wouldn't overwrite history, you'd create a new one. That's the many worlds version. Every action branches the universe. The flux capacitor's 1.21 gigawatts. That's roughly the output of a small nuclear reactor over a second. Enough to vaporise the car but not propel it through time. Fun, yes. Accurate, no. It did, however, teach a generation the differences between space and space-time, and that was a big win for physics. What about the Terminator series? Cyborg assassins, causal loops, the future creating its own past. The first two films are built on the bootstrap paradox, the idea that an event causes itself. Skynet exists because its future technology was sent back to start its own creation. That's surprisingly consistent with Novikov's self-consistency principle. If closed time-like curves exist, paradoxical events simply have probability of zero. So the Terminator's loop isn't impossible, it's just self-contained. Still, the timelines in later sequels split endlessly. That's closer to the many worlds again, each intervention spawning a new branch. From the physics point of view, the first movie is paradox-proof. What about Interstellar? In this film, Christopher Nolan clearly did his homework. Physicist Kip Thorne shaped the script and the equations. The black hole gargantua follows real general relativity, spin, light bending, and time dilation. The 1 hour equals 7 years ratio checks out if you orbit close to a supermassive Kerr black hole. That's a real gravitational time travel. The Tesseract scene, Cooper sending messages through time using gravity, that's where the science drifts a little more into metaphor. There's no known mechanism that lets gravity transmit discrete messages through higher dimensions, but the visualization of a 4-dimensional space-time volume was brilliant. It captured all the moments existing simultaneously, the block universe idea, and it made universes feel relatively emotional. That's rare in cinema. What about Tenet? Time running backwards, bullets unfiring themselves, essentially entropy reversing. Christopher Nolan again, but this time he didn't get the physics right. This film is pure metaphor. In real thermodynamics, entropy is statistical. You can't reverse it for a single person without reversing every atom in the universe. Even your lungs wouldn't work. Inhaling inverted air would suffocate you. Still, Tenet gets one concept right. Time symmetry in physics. The fundamental equations, Newton's laws, Schrodinger's equation, Maxwell's equations, work the same backwards as forwards. It's only entropy that really breaks the symmetry. So Tenet isn't total nonsense. It's poetic exaggeration of a microscopic reversibility. Think of it as philosophy in motion, but not physics in action. What about Doctor Who? Doctor Who treats time like an elastic band. The show's strength isn't accuracy, it's exploration. The TARDIS is basically a local bubble of warped space-time. The problem, the energy required, would exceed the mass energy of the observable universe. Still, the idea of fixed points in time, events that can't be changed, echoes the Novikov principle. Doctor Who uses storytelling to teach temporal ethics. Just because you can change the past doesn't mean you should. Physics agrees with that sentiment, even if it doesn't agree with the sonic screwdriver. Avengers Endgame. The Marvel Universe actually handles time travel better than most. Instead of one changing timeline, they went full quantum multiverse. Travel to the past creates an alternative branch. It doesn't rewrite your own. That's straight from the many worlds interpretation of quantum mechanics. Tony Stark's time GPS? Nonsense, but the logic was right. The one part that bends physics is the return mechanism. Jumping between quantum branches would require universe-scale coherence. But at least Endgame avoids paradoxes, and that's more than most sci-fi has actually managed to do. Looper. Rian Johnson's Looper mixes both models. Assassins send victims back for disposal. When the older version of a man interacts with his younger self, the timeline shifts instantly. That's the single mutable timeline model again. Real physics says you can't instantly rewrite your own history. You'd create a new branch, not overwrite the old one. Still, the moral core, closing your own loop, fits Novikov's logic. In that sense, Looper is paradox-safe storytelling. What about the time machine? H.G. Wells is arguably the man who started it all. A Victorian scientist builds a brass contraption and rides into the far future. The genius, Wells writes it well before relativity exists, yet he describes time as a dimension long before Einstein did. That intuition was decades ahead of physics. The 2002 remake, however, added a paradox. The hero can't change the event that motivates him to build the time machine. Every attempt to save his fiancée causes her death in another way. That's pure self-consistency principle. It's also hauntingly logical. What about the film 12 Monkeys? Bruce Willis, a plague, a loop that closes perfectly. No branches, no rewrites, just inevitability. That's textbook Novikov consistency again. Everything happens because it already did. From a physics standpoint, 12 Monkeys is one of the few films that gets time travel right. From a human standpoint, it's terrifying because it means free will might just be an illusion. What about the film Predestination, 2014? If Novikov wrote a screenplay, it would look a lot like this, I think. A time agent hunts a bomber, only to discover he is every major character in his own story. The film's closed loop is absurd, and yet perfectly consistent. It obeys every rule of the Novikov model. Causality is intact, paradoxes are zero. Hard science, no. Logical, entirely. So, which film or series got closest? For hard physics accuracy, probably Interstellar. For logical consistency, probably 12 Monkeys and Predestination. For public education, probably Back to the Future. For pure imagination, probably Doctor Who. Each story bends the rules differently, but every one of them asks the same question. Can cause and effect survive curiosity? It's the real heart of time travel. Because whether it's a DeLorean or a wormhole or a black hole, they're all doing the same thing. Physics does not hand us a paradox-free, low-energy way to visit our own past. It gives us robust, tested methods to visit the far future, move fast, or linger deep in a gravitational well. If backward travel exists at all, it either hides behind energy scales and exotic matter we cannot reach, or it is filtered by quantum consistency so strictly that only self-consistent or branch-splitting histories can ever occur. Forward time travel is not only possible, you're doing it right now. And relativity lets you do it faster or slower with speed or gravity. Backward time travel is not outright forbidden by our best equations, but it hides behind extreme energies, exotic matter, and a wall of quantum consistency. If it is ever practical, then somewhere, somewhen, it already is, and the reason we don't see Taurus might be the best evidence for chronology protection we'll ever get. I hope you've enjoyed this travel through the real science of sci-fi and time travel. If you have, then please subscribe, and I'll see you in the next video.